Welcome back, everyone. Today we start chapter 2, forecasting. This is where we start putting numbers on supply chains. All right, forecasting simply uses historical data to predict the future. And the most common application, predicting demand. Get it right, you order the right inventory. Think of an electrical component distributor stocking 50,000 parts. Over forecast, capital sits on shelves. Under forecast, a production line shuts down waiting for, a 5-cent component. Famous quote from Niels Bohr: prediction is very difficult, especially if it's about the future. He's joking. He's also serious. Remember from chapter 1, plan, buy, make, move, distribute, sell. Forecasting lives in plan. Everything downstream depends on it. Alright, forecasting problems are classified by time horizon. 3 categories basically. Short-term, days to weeks. Production scheduling, inventory, meaning how many should be buy or make next day or next few weeks. Intermediate term, weeks to months. Resource and workforce planning. Long term, years out. Capacity expansion, new facilities. These long-term decisions are made executive leaders because of the capital expenditures or potential impacts. Different horizons, different decisions, different people. Now, 5 fundamental truths about forecasts. First, forecasts are, almost always wrong. Plan for error. You may get lucky once and say your company will sell 107 of these items next month, and you might hit the nail on the head. Now, what happens if you forecast 108 in this scenario? Then you're wrong, but you're super close. The objective of the forecasting is not really get the exact number, but be as close as possible to it. Second, a good forecast gives a measure of error. 100 units plus or minus 15. Third, aggregate is easier than individual. Total iPhone sales next quarter is more accurate than one model in one store. And fourth, longer horizon, less accurate. Weather forecast for tomorrow's is going to be more accurate than the next week. Similarly, next week's weather forecast is going to be more accurate than forecast for the next month. Fifth, don't ignore known information, new events, a competitor failing, a new tariff. Factor those in manually. All right. Forecasting methods split into 2 camps. Subjective and objective. Subjective is basically based on human judgment. 4 common ones. Salesforce composites. Salespeople talk to customers daily, aggregate their estimates into a forecast. Customer surveys. Ask customers what they plan to buy. Jury of executive opinion. For new product launches with no historical data, executives reach consensus. Delphi method. Poll experts in iterative rounds, seeing anonymized opinions. Powerful for long-term technology forecasts. Now, expert opinion shines when there's no historical data. New product launches, for example. Famous case, Moore's Law. In 1965, Gordon Moore, co-founder of Intel, observed that transistors in an integrated circuit were doubling every 2 years. He predicted that would continue, and that prediction held for almost 5 decades. The entire electronics industry organized around it. Now, not exactly anymore, as transistors approach the size of atoms, the physics gets harder. Less, and even the most successful expert forecast eventually breaks. All right, now objective or quantitative methods. Objective forecasting derives forecasts from analyzing data. 2 types, time series models and causal models. Causal models first. All right. The equation y equals f of x sub 1, x sub 2, x sub 3, all the way to x sub n. The thing you're forecasting y is basically a function of other variables. The x's are external factors that influence y. Causal models pull data from sources other than the series you're predicting. Classic example, predicting gross domestic product GDP using consumer spending, government spending, business investment, and net exports. And we won't dwell on causal models. The bulk of our time goes to time series. All right, time series models, the workhorse, they use only, past values of the thing you're predicting. No external variables, just history, because they don't need any other information. They're sometimes called naive models. Don't let the word fool you. They're the backbone of most demand planning systems. And the time series is just data drawn at discrete points of time, usually equally spaced. daily sales, weekly orders, monthly demand. All right, when you look at time series data, you're trying to identify, well, patterns, identify them, project forward, make a forecast. First pattern, trend, the tendency of a series to show stable growth or decline over time. Two charts on the slide. Left, increasing linear trend, demand goes up steadily along a straight line. Right. Curvilinear trend, the rate of growth itself accelerates, and trend can be linear or non-linear, positive like a hot product, negative like typewriters. Now, second pattern, seasonality, a pattern that repeats at, fixed intervals, daily, weekly, monthly, yearly. Yearly is most familiar. Ice cream spikes every summer, right? Heating oil peaks every winter. Christmas trees sell in December. But seasonality isn't only yearly. The electricity charts show daily seasonality. Demand rises in the morning, peaks in late afternoon, drops overnight. Same pattern every day. On the right of the slide, you can have seasonality and trend at the same time, basically. Wavy line plus upward tilt. Real demand often looks exactly like this. All right, two more patterns, cycles, similar to seasonality, but length and magnitude can vary. Period usually longer than a year, swings irregular. Classic example, business cycles, growth, peaks, recessions, troughs, recoveries. They happen, but you can't set your watch by them. And last pattern, randomness, just noise. Real data mixes patterns, some trends, some seasonality plus noise. Our job is to separate them. All right, now error metrics. The forecast error at time t is basically the difference between the forecast and the actual demand at that period. Now, two formulas on the slide. First, E sub t equals F sub t minus tot minus D sub t. Multiple step ahead error, forecast made tau periods ago. Second, E sub t equals F sub t minus D sub t, one step ahead error. And that's the one we'll use most. Positive means, over forecasted. Negative means under forecasted. All right. Three error metrics. When we do these calculations, you will see that we are taking absolute value or squaring of numbers. The reason is that we do not want positive and negative forecast error to cancel each other. For example, if I said forecast is 200 and actually demand is 150, the error would be 50. Next time, just assume my forecast has an error of minus 50. What would be the sum of 50 plus minus 50? 0. So the average would be 0 divided by 2 forecast I had, which is equal to 0 error. But in fact, I was off by 50 each time. That is why error metrics consider absolute value or square of an error. Now, let's look into the metric.s first. MAD, mean absolute deviation. MAD equals 1 over n times the sum from I equals 1 to n of the absolute value of E sub I. Average of the absolute errors, basically. MSE, mean squared error. MSE equals 1 over n times the sum of A sub I squared. Squaring makes large errors count much more. MAPE, mean absolute percentage error. MAPE equals 1 over n times the sum of the absolute value of A sub I divided by D sub I multiplied by 100. Error as a percentage of actual demand. All right, let's apply these to a real example. Artel manufactures static random access memories SRA AM's two plants, Austin, Texas, and Sacramento, California. And each plant manager forecasts their plant's weekly production yield in percent. Based on 6 weekly forecasts, management wants to know which manager is the better forecaster. Now look at the table. P sub 1 is manager 1's forecast. O sub 1 is the actual at plant 1. P sub 2 and O sub 2 are the same for manager 2. Take week 1 for example. Manager 1 forecasted 92. Actual was 88. Error of 4. Manager 2 forecasted 96. Actual was 91. Error of 5. Next slide, we calculate MAD, MSE, and MAPE. All right, same table now filled in. Let's walk through one calculation of each metric. Now, MAD for manager 1, using P sub 1 and O sub 1. The absolute errors across 6 weeks are, 4, 1, 2, 7, 3, and 0. sum is 17, and MAD1 equals 17 divided by 6, which is 2.83. MAD for manager 2 is 18 divided by 6, 3.00. Manager 1 wins on MAD basically. All right, MSE for manager 2 using P sub 2 and O sub 2. Squared errors are, 25, 0, 4, 9, 16, and 16. Total 70. MSE2 equals 70 divided by 6, 11.67. MSE1 is 79 divided by 6, 13.17. And manager 2 wins on MSE. Why? Well, manager 1 had one bad week, error of 7. Squared, that's 49, dominating the total. MSE is more sensitive to large errors. MAPE for manager 1, I mean each error divided by actual demand, absolute value, summed and averaged. Manager 1's MAPE is 3.25%. Manager 2's is 3.36%. Manager 1 wins on MAPE, final scorecard. Manager 1 wins on MAD and MAPE. Manager 2 wins on MSE. The metric you choose is itself a business decision. If we are comparing two forecast results, the one with smaller MAD or MSE or MAPE is better compared to higher. We only compare MAD values with each other, so no apple versus orange comparison to choose the best one. Moving average method. All right, now actual forecasting methods, stationary data, no trend, no seasonality, just bouncing around a constant level. First, the moving average. A moving average of order n, written MA of n, is basically the arithmetic average of the most recent n observations. The formula f sub t equals 1 over n times the sum from I equals t minus n to t minus 1 of d sub I. I mean, your forecast for time t is 1 over n times the sum of the last n actual demand values. So if we are doing moving average monthly using 3 periods, our forecast for April is going to be the sum of actual demand in March, February, and January divided by 3. Same way, if we are forecasting May, it will be equal to the sum of actual demand in April, March, and February divided by 3. Moving average in action. Here's an example about the engine failures. We have quarterly data, quarters 1 through 8. MA of 3 starts at quarter 4. We need 3 quarters of history. The forecast for quarter 4 is the average of quarters 1, 2, and 3. 200 plus 250 plus 175 divided by 3 gives 208.33. Remember, because it is MA of 3, we cannot forecast quarter 3 demand because we only have quarters 1 and 2 at that point. Now, 3 practical points. Multiple step ahead at time t, MA of n gives the same forecast for next period and the period after, flatlined into the future. Storage, you keep n data points around. Outliers, a weird point affects MA of n for exactly n periods, then falls out. Larger n, slower to wash out outliers. Moving average lags trend. All right, critical limitation. Moving average does not handle trend. The example, demand rises perfectly linearly from 2 up to 24. And MA of 3 and MA of 6 both lag. In quarter 12, actual is 24. MA of 3 forecast 20. MA of 6 only 17. The forecast is consistently below actual, pulled down by older, smaller values. Bigger N further behind. Bottom line, MA is for stationary data only. For trend, different method. Coming in part 2. All right, second method for stationary series, exponential smoothing, one of the most widely used methods in, industry. Pay close attention. Equation 1, f sub t equals alpha times d sub t minus 1, plus, in parentheses, 1 minus alpha times f sub t minus 1. Each piece, f sub t, is the forecast for time t. D sub t minus 1 is basically last period's actual demand. F sub t minus 1 is last period's forecast. Alpha is the smoothing constant, a number between 0 and 1 that determines weight on the new observation versus the old forecast. I mean, your new forecast is a weighted average of the most recent actual value and your previous forecast. Now, equation 2, f sub t equals f sub t minus 1 minus alpha times e sub t minus 1. Your new forecast equals your old forecast adjusted by alpha times the most recent forecast error. Over forecast last period, adjust the new forecast downward. Equations 1 and 2 are mathematically equivalent. The next slide derives equation 2 from equation 1. All right, now the math. This shows where the word exponential, comes from. Now equation A, f sub t equals alpha d sub t minus 1 plus 1 minus alpha times f sub t minus 1. That's our standard formula basically. Equation B, well, same formula shifted back one period. F sub t minus 1 equals alpha d sub t minus 2 plus 1 minus alpha times f sub t minus 2. And substitute equation B into equation A. Replace f sub t minus 1 in equation A with the right hand side of equation B. After substituting, we get, f sub t equals alpha d sub t minus 1 plus alpha times 1 minus alpha times d sub t minus 2 plus 1 minus alpha squared times f sub t minus 2. All right, keep substituting backward forever and we get the general form. F sub t equals the sum from I equals 0 to infinity of alpha times 1 minus alpha to the I times d sub t minus I minus 1. More compactly, f sub t equals the sum of a sub I times d sub t minus I minus 1, where the weights a sub I equal alpha times 1 minus alpha to the I. Now key insight, those weights satisfy a sub 0 greater than a sub 1 greater than a sub 2 all the way down. I mean, the weights decline geometrically. Recent data gets more weight, older data gets less, bottom line. Well, exponential smoothing applies a declining set of weights to all past data. That's the exponential decay that gives the method its name. All right, look at the bar chart. This is what exponential smoothing actually looks like. Horizontal axis is, the age of the data. Vertical axis is the weight a sub I applied to that data point. Now, notice the shape. The most recent observation, I equals 0, gets the largest weight, the next smaller still, decaying towards 0, but never reaching 0. That's the geometric decline we just derived. And compared to moving average, MA gives equal weight to the last n observations, 0 to everything before. Exponential smoothing gives a smooth declining weight to everything. MA is a window, ES is a fade. All right, let's apply both methods. Quarterly aircraft engine failures at, a military base. 3 forecasts on the table, basically MA of 3, ES with alpha of 0.1, and ES with alpha of 0.9 in the exponential smoothing. Forecast for quarter 1 values is an assumption. Due to formula for exponential smoothing, we need to have an initial forecast to start. Here we are assuming that the initial forecast is equal to the demand in quarter 1. This assumption allows us to calculate the forecast from quarter 2 to quarter 8 using the exponential smoothing. Now look at the MSE values. ES with alpha of 0.1, MSE of 2594.8. And the forecast hardly changes quarter to quarter, very stable. A stationary forecast. ES with alpha of 0.9, MSE of 3297.3. The forecast jumps around, variation in forecast, same data, same method, different alpha, wildly different behavior. So how do you choose alpha? 3 lines on the chart. Actual demand plus ES with alpha of 0.4 and ES with alpha of 0.1. Now 3 rules: smaller alpha, more stable forecasts, and higher alpha, more variation, tracks demand more closely. The trade-off: larger alpha tracks responsively, but stability from a smaller alpha is often more desirable for planning. Stable forecasts let purchasing, production, and warehousing actually plan. Forecasts that jump around create chaos. Typical industry alpha values fall between 0.1 and 0.3. Also, you can find the best alpha values looking at the past performance based on error metric. For example, alpha equal to 0.1 is a better value compared to alpha equal to 0.9. Guess why? Because MSE is smaller, so for alpha 0.1 it is more accurate. All right, final slide, side-by-side comparison. Similarities, both methods assume, stationary demand, both depend on a single parameter, n for moving average, alpha for exponential smoothing. Both lag behind the trend if one exists. Differences. Now, ES is a weighted average of all past data. MA only uses the last m periods. Outliers fall out of MA after n periods. In ES, an outlier never fully disappears, it just fades. MA has a storage cost, ES only needs the previous